Welcome. This video will provide a technical deep dive into the architecture of Apache Airflow. We will dissect the individual components, understand their functions, and explore how they interact to form a cohesive distributed system for workflow orchestration. The Airflow ecosystem. A modular foundation. Airflow is not a single monolithic application, but rather a collection of Python-based services that work in concert. This modular design is key to its scalability and flexibility. At its core, the architecture revolves around a central metadata database, which acts as the single source of truth for the entire system. All other components, including the scheduler, Webserver, and workers, are stateless services that communicate by reading and writing to this database. The core components, required for operation. Let's break down the essential components of any functional Airflow installation. The scheduler. This is the daemon process that is the brain of the Airflow system. Its primary responsibilities are threefold. First, DAG parsing. The scheduler constantly scans the designated DAGs folder, parsing the Python files to identify new or updated workflows. Second, scheduling. Based on a DAG's defined schedule, the scheduler creates new DAG runs and corresponding task instances within the metadata database. Third, task submission. It monitors the state of all task instances, and when a task's dependencies are met, it submits that task to an executor for execution, the metadata database. This is the persistent backend of Airflow. It is the centralized repository for all stateful information, including DAG and task instance states, DAG schedules and run history, connections, variables, and other configuration settings, and XCOMs, the small pieces of metadata passed between tasks. For any production environment, a robust external relational database like PostgreSQL or MySQL is a strict requirement. Using an in-memory or file-based database like SQLite is not supported for distributed or high-concurrency workloads. The Webserver. This component provides the graphical user interface and a REST API for interacting with Airflow. It is the primary tool for visualizing DAGs and their dependencies, monitoring the status of running and completed tasks, triggering DAG runs and managing connections or variables, and viewing logs and debugging task failures. The Webserver is a stateless service that pulls all its data directly from the metadata database. The DAGs folder. This is the location on the file system where your workflow definitions, written as Python files, reside. It is a critical architectural requirement that this folder and its contents be accessible and identical to both the scheduler and all of the workers. This is typically achieved through a shared volume, object storage synchronization, or container image bundling. The execution layer, making it happen. The executor is the mechanism the scheduler uses to run tasks. It is a configuration property, not a separate component. The choice of executor dictates the deployment model and scalability of your Airflow environment. The local executor. This is the simplest executor. It runs tasks as separate processes on the same machine as the scheduler. It is suitable only for development or low concurrency environments, as it offers no horizontal scalability or fault tolerance. The Celery executor. This is a popular choice for distributed environments. It uses an external message queue, such as RabbitMQ or Redis, as an intermediary. The scheduler dispatches tasks to this queue, and separate Celery workers pull tasks from the queue for execution. This architecture allows for horizontal scaling by simply adding more worker nodes. The Kubernetes executor. This is a modern, cloud-native executor. Instead of relying on a pre-provisioned pool of workers, the scheduler dynamically creates a new Kubernetes pod for each individual task. This provides excellent resource isolation, dynamic scaling, and fault tolerance by leveraging Kubernetes orchestration capabilities. The triggerer. A newer optional component designed for efficiency. The triggerer handles deferrable operators, tasks that are waiting for an external event. Instead of a worker being blocked while it waits, the task is deferred to the triggerer, which uses a highly efficient asynchronous event loop. When the external event occurs, the triggerer wakes up the task, and it is sent back to a worker to complete its final steps. The workflow lifecycle. From code to completion. Let's trace the journey of a single task. First, parsing. The scheduler parses the DAG file from the DAGs folder and identifies the task. Second, scheduling. The scheduler observes that all upstream dependencies for this task are complete. It then creates a queued entry for the task instance in the metadata database. Third, dispatch. The executor checks the database for queued tasks. In a Celery-based setup, it publishes a message containing the task's information to the message queue. Fourth, execution. A free Celery worker consumes the message, spins up a new process to run the task, and begins its execution. Fifth, state update. Throughout its lifecycle, the worker updates the task state in the metadata database, from running to success, failed, or skipped. Architectural considerations: high availability and scalability for production deployments. Ensuring a robust, highly available system is paramount. Scheduler high availability. You can run multiple schedulers simultaneously. They use a database-backed leader election mechanism to ensure only one scheduler is actively creating DAG runs and submitting tasks, while others stand by as hot spares. Webserver high availability. This is achieved by running multiple Webserver instances behind a load balancer. Since the Webserver is stateless, this is a straightforward way to ensure uptime and handle increased traffic. Metadata database. High availability. This is the most critical point of failure. Your metadata database should be deployed using a highly available configuration with replication and automated failover, such as a PostgreSQL cluster. Scalability. Horizontal scaling is a key feature of Airflow. You scale by increasing the number of worker nodes, which is handled gracefully by the Celery and Kubernetes executors. The metadata database, however, can become a bottleneck under extremely high loads and must be a part of your scaling strategy. This concludes our technical overview of the Airflow architecture. We hope this provides you with a solid foundation for designing, deploying, and managing your own robust Airflow environments.